Hey, we're going to look at today the different ways that a function may or may not have a derivative. And there's four special categories that we can look at. And anytime you're on a graph, you'll be able to see these four things. You'll know right away there's not a derivative at that specific place. So let's just dive right on and look at them. I've got four graphs here. One shows a corner. And so if we just check this guy out, we've got what looks like let me get rid of that. What looks like a uh, absolute value graph comes in, bounces off. So at this point 0 right here, we've got a corner. And anytime you have a corner, you don't have a derivative. So we cannot take a derivative at that particular point. Where else may we not? Well, on this graph right over here, which could be like a little bouncer action. So it looks like this. It's got a cusp. Again, it's a little corner point, but when it kind of folds in and bounces, and it looks like almost kind of like a fold of paper or something like that, or like the square root graph of a square root with a mirror image over the y-axis. This would be called a cusp, and we can't take a derivative there either. So what about a vertical tangent? Well, we come across vertical tangents every now and again, and a vertical tangent would look like this guy, where you're cruising along and everything's great, but then right here at 0 we go straight up and down. So right here we're straight up and down, and where we're straight up and down, that's a vertical tangent, which means that the change in x is 0, which is in a denominator, and you can't divide by a denominator. So remember, when you're taking a derivative, you're looking at a slope, and we cannot have a vertical tangent. Can't do it. Lastly, it's a discontinuity, and so this would look something like, maybe absolute value x over x or something like that. But notice again, at the point 0, 0, there's just no way for us to take a derivative at this point because we're approaching two different numbers. Remember, to have a derivative, you've got to approach the same exact y value. And we don't do that when we have a discontinuity of this type. And this is, more specifically, this isn't just a discontinuity, it's a jump discontinuity. So, so that's one of the discontinuities. That is one of the big discontinuities that we can't have a derivative at. But these are just a few examples of where you cannot have a derivative, and there's really not tons and tons of different things to memorize. We're just looking for a corner, a cusp, a vertical tangent, or a jump discontinuity. So what we're going to do on this problem then is we're going to take a graph that they've given us that f of x equals x minus 2 plus 3, and we're looking at absolute value of x minus 2, and hey, guess what? There's a place where this is not differentiable. There's a lot of places it is, but there's one place it isn't. And when we're dealing with absolute value, the one place that we're not differentiable is right where we're at our vertex. So we need to figure out what our vertex is, and the -2 and the 3 are the giveaways for this. So think about inside the absolute value, what value of x makes a 0? So if I just go, x minus 2 equals 0, what value does that give me? 2. And then think about this, when x minus 2, when that is 0, what value of y do I have? And we're looking at a vertex at the point 2, 3. Now here's the thing. You can graph this as well on your calculator. Graph y equals absolute value x minus 2, close absolute value plus 3, and take a look. Where your minimum occurs, where that v part of your graph is, your vertex, that is where we're not differentiable. So when I ask you, hey, find all the points in the domain where we aren't differentiable, we're not differentiable at this point right here at 2, 3. We are not differentiable. Okay, we cannot take a derivative at that point. So some other things that we can do with our calculator that are pretty fun is we can use what's called Ender to calculate a numerical derivative. And I'll put a calculator up right now and you can see what that looks like. And it's really easy, and this gives us an actual numerical value for the derivative of x cubed when x is 2. And so there's how you do it, and you can do it with Inspire and the 84s and the 83s. So it's really nice. Use Compute Ender on your calculator to find the numerical derivative of x when x equals 0. Why is your calculator not telling you the truth? And the reason that happens is your calculator is trying to find, it's trying to do the math, and you end up fooling your calculator at that specific spot. So it's going to tell you one value, but you have to be smart enough to know that when you are working with absolute value of x at 0, that's where we're going to get our vertex. And wherever that vertex happens, no derivative can occur there. So play with your calculator for a little bit. Ender is really, really nice. It's really, really handy, and it really gives us a really good, accurate depiction of what it might look like with the numerical derivative. All right, so here we got a couple of really cool theorems that we can use as part of our derivative process, and you kind of have seen these before with limits and things like that, but they make sense once you see how everything works and what we just talked about with corners and cusps and vertical tangents. So here we go. One is differentiability implies continuity. What does that mean? That means that if we can take a derivative, we're continuous at a point. So if some function has a derivative at a specific value of x, then we can take a derivative at that value of x because we're continuous at that value of x. And the other one is the intermediate value theorem, and this just says that if we look at some x value on the derivative and some second x value on the derivative, then all the points in between have to have a specific y coordinate value. And so basically that also is just telling us, hey, you know what, this is also a continuous function. So show that the given function is not the derivative of any real function on -1 to 1. And all we're going to do is look at this guy, and if you think about if you think about this, we're going to let's just graph it. So here we've got this graph. And if we graph the first part, right here, we'll graph it in this pink color, we're going to be equal to 0 from -1 to 0. So let me give myself some coordinates here. -1, 1, 2, -2. So here's what I've got going, and then if I go from -1 to 0, I have a line that looks like this. And then when I go from 0 to 1, I'm going to have a line that looks like red. We'll do this guy in a red color. So he's going to be like this. And so the question is, show that the function is not the derivative of any real function. Well, why is it not the derivative of any real function? Because right here, when x is equal to 0, we have a discontinuity. And since we have this discontinuity, we cannot have a derivative. Now, if we were only looking from -1 to 0, so if we were to just look from -1 to 0, just from here to here, we can take the derivative because we have a slope. It's not a corner or cusp. It's continuous. If we look at the red equation, if we just start right here at 0 and go to 1, we would have a derivative. But because we go from -1 to 1, and we've got this point of discontinuity at 0, there is no derivative at this particular location. All right, so here we have an example. This is from your book, question number 1. It says compare the left and right hand derivatives and show that at the specific point, which in this case is 0, 0, that the function is not differentiable. What does that mean? That means when we look at the derivative at the point 0, 0, and we look at the function from the left, which is y equals x squared, and we look at the function from the right, which is y equals x, that they aren't going to equal the exact same number. Remember, to have a derivative at a specific point, then you have to look at the values of the slopes coming from the left and the right. And if those slopes have different values, you cannot have a derivative. So we're just going to run the limit process on both of these guys here. We're going to run the limit as h approaches 0 of f of x plus h minus f of x all over h. And we're going to do this for both parts. We're going to do this for x squared and for x. So in pink, we'll work with y equals x squared. And when you put 0, 0 in, the point you're going to get is 0. So here we go. F of x plus h, in this case, x is equal to 0. So we're going to have 0 plus h squared minus 0 over h. And we're going to look at this limit as h approaches 0. Clean this guy up a little bit. You're going to end up with h squared minus 0 on the top. You can factor an h out of the top and bottom, which gives us this. And when you substitute in 0, we get 0. So the derivative at 0 is 0. Okay? What about that other guy? Well, let's look at him. So if we look at the limit for y equals x, and also when we put x in, you get 0. So we're going to look at the limit of 0 plus h minus 0 all over h, and we're going to look at this limit as h approaches 0. Which is going to give us on the top h minus 0 over h, which is equal to h over h, which reduces all the way down to 1. So this guy, the derivative at 0, equals 1. So coming from this direction, y prime equals 1 at 0. Coming from the other direction, y prime equals 0. So since these two numbers are not the same, since I have a 1 here and since I have a 0 here, those numbers are not the same, which means that I am not going to have a derivative at that specific spot.